Find the maximum volume of a box that can be made by cutting out squares from the corners of an 8-inch by 15-inch rectangular sheet of cardboard and folding up the sides. Justify your answer. Here's our 15 by 8 cardboard right here. We're cutting out squares of equal length from each corner of our cardboard box. Now, once these squares are cut out, we'll then fold up the resulting sides to create a box. Now, the volume is what we are trying to maximize here. We're trying to maximize the volume. So the first step here is we need to create a model for the volume of the resulting box. And of course, the volume of a box is length times the base times the height of the box. Now, the length of this box was 15 before we cut out the sides. But after we cut out the sides, we cut one x from this side and another x from this side. So the resulting side altogether now is this right here, which is 15 minus x minus x. So in other words, the length is 15 minus 2x. Likewise, we're looking at this little piece of strip right here for the base of this box. The former base was 8, the former width was 8, but then when we cut off two of these x's, our new base is 8 minus 2x. And finally, when we fold up this side right here and this side, that gives us the height of this box. And of course, the height is just the length of this square, x. Well, taking the derivative of this is going to be kind of difficult. So why don't we just expand it out? And of course, I've already done that. V is equal to 4x cubed minus 46x squared plus 120x. Don't believe me? Multiply it out yourself. Okay, well, let's take the derivative of v so that we can do our first derivative analysis. We want to maximize the volume. So let's see what value of x we have to cut out from the corners in order to create the maximum volume. To do that, let's take the derivative of v. V prime is equal to 12x squared minus 46 times 2 is 92x plus just 120. This always exists, so we will have no critical points where the derivative fails to exist. So let's set this equal to 0. To solve this, let's first factor out 4. So here we have 4 times 3x squared minus 23x plus 30. And this is all equal to 0. We can factor this down actually. This is 4 times 3x minus 5 times x minus 6, and this is all equal to 0. So we have critical points at x equals 5/3 and at x equals 6. Let's do our first derivative analysis on v prime. So here is 3 over 5, and here is 6. Let's look to the left of 3 over 5. How about 0? Positive, negative, negative gives us a positive number to the left of 3 over 5. Let's check between 3 over 5 and 6. How about 2? Positive, positive, negative. So this is negative in here. And of course, to the right of 6, how about 7? We have positive, positive, and positive. That's positive out here. So that means that v has a relative max at x equals 3 over 5 because v prime is changing from positive to negative. And v has a relative min at x equals 6 because v prime is changing from negative to positive. We're more interested in this one right here, 3 over 5. That's the cool one. Alright, so we know exactly where, at what x value, the volume is maximized. Now all we have to do is just plug 3 over 5 back into v. And when you plug 3 over 5 in, you get that the volume is equal to 90.741 inches cubed. And this is the maximum volume of a box that can be made by cutting out squares from the corners of an 8 by 15 inch cardboard sheet. We got this, of course, by doing our first derivative analysis, getting 3/5 as a relative max and plugging that back in to the volume function.